Hello everyone. My name is Zsolt Kocsi and I'm an Android engineer at Badoo. Badoo is a dating app company. Not everyone knows we don't just create our flagship dating app, but we also provide the technology to a bunch of other apps as well. So we create Bumble, which is a women-first approach to dating. Chappy, which is a gay dating app. Lumen, the first dating app for people over 50. And Quack, an app where you can connect to other people through your friends. We also expect a whole lot of new apps in the not-so-distant future. Our biggest and oldest app is, of course, still Badoo, with its more than 420 million registrations worldwide. Both its size and the need to reuse technology between different apps create the pressure to make our architecture better and more scalable. Today I'd like to talk about our past couple of years in terms of Android architecture, mentioning some of the key problems that we faced on the way. Our first problem where this story starts is about state. So historically, a couple of years ago, we mostly had MVP all around the app. Now, if you don't follow any architectural patterns, then MVP is definitely a step forward. Problem is, it's quite a small step. Many devs I talk to actually get stuck here with their applications. If you are developing something small with only a few screens, sure, don't overdo it. But as our app grew bigger, MVP didn't really scale well, and we started looking for other solutions. When clean architecture became the next trendy thing, we were among the first to try it. Well, there's nothing wrong with it in itself, but we soon realized that our main problems were not even the ones that it offered a solution for. So for example, take this image. This is from an archived library of ours. It describes the flow between two endpoints of a view and a data source. And as you can see, there are many mediators here. And while it's useful to have abstractions, at what point we asked ourselves, are these the right abstractions? Clean architecture's main promise was that we would be able to easily swap out presentation layer or data layer implementations without touching anything. That's really useful, isn't it? After all, do you know how many times I needed to replace presentation or data layer since my first day at Badoo? Well, exactly 0 times. I'm not saying that this is the general case. It might be useful for you, but at least for us, the benefits of this approach, while sounding good in theory, turned out to be negligible, while the increased number of abstractions just made it more difficult to follow through code. On the other hand, a huge amount of our bugs were state-related, hard-to-track-down issues. Our apps are complex and massively asynchronous, and there's a good chance that some series of events can set your variables in a combination that you hadn't thought of before. And then you have a bug. There's also a good chance that the same series of events might never happen to you again. And then it's really difficult to track it down. Anyone had this experience with QA? So you ask for a crash log, but there is no crash. There is a video recording of the bug, but you can never reproduce it. So what we realized we needed was a centralized immutable state. This idea came to us from the web dev world when Redux became a thing. Hopefully these words like Redux, MVI, and immutable state are not completely new to most of you. But just in case, very quickly, MVI means mod view intent. And the idea is that interactions with the view create intents, which change the model, which is reflected in the view. And it's a unidirectional data flow. And it almost always comes with an immutable state and the reducer. So now you have a single point of mutation where changes can happen, which means fewer places for things to go wrong. It makes it virtually impossible to get into unexpected states. And it makes it easy to understand how your state can change. The problem is, when we wanted to try this, there was no ready-made solution for Android at the time. And we needed to figure it out for ourselves. Because the immutable state part is only the beginning, and so many things are just missing from the picture yet. The first steps were quite rough. We had something that was inspired by Redux, but it was a mixture of everything. Some parts legacy MVP code, some parts clean architecture, halfway refactored, some immutable state stores, and RxJava. Also, it was before Kotlin became officially supported on Android, so you can imagine the mess of it. It was really ugly, but on the other hand, it was really promising. It was easier to understand state changes, and our state-related bugs quickly became a thing of the past. On the other hand, we needed to figure out a good structure for this approach. So we experimented with multiple approaches for almost 1.5 years. And we open source the best tools that we created during this time and put them in a library project on GitHub called MVI Core. So getting back to the problem of state management, let me show you our version of it before moving on to other problems. The big picture is that we have state machines, which we named features. The name reflects that they are designed to encapsulate all state-related business logic of a business feature. A feature can receive a wish as an input, where wish is the intent part of model view intent, and it can produce a state as an output. In its simplest form, the feature can have a single reducer, which will take the current state and the incoming wish and create a new state based on that. In code, it looks like this. So let's say we have a really simple state, which just stores a counter. And let's say we have two wishes how to change this state, either to increment the counter or to multiply it by some value. Let's create the reducer. When invoked, it will have access to the current state, the incoming wish, and it's expected to return a new state based on those. So let's take the wish, and if it was increased counter, we just create a new state where the counter is the current one plus 1, or if it was multiplied by, then multiplied by the value we get from the wish. Kotlin sealed classes here are super useful, as you get compile time safety to implement all the branches in the reducer. Now all we have to do is just create a feature with the initial state and the reducer passed in the constructor. Unfortunately, having a simple state machine with the reducer is just the beginning, and it only opens the door for further questions. The most important is probably how should we organize handling side effects. There are many approaches to this, and it was not obvious at first which one would be the best for us. The first approach is just to implement side effects externally and not put them inside the state machine. So imagine that we want to load some data from the web. We add the flag to the state to indicate loading. We add another one to indicate some error. And we add the field to hold the payload when it arrives. Now, wishes to change this state could mean that we started loading, finished with success, or we had some problem. Implementing the reducer, when the wishes started loading, we just flip the loading flag in the state to true. If it was success, we reset the loading and any possible error to false and set the payload. And if it failed, then we set the loading to false and also the error to true. The problems with this approach are that, first of all, the whole async logic is not an encapsulated part of the feature. Secondly, now it's possible to set the feature into, for example, loading state just by sending it that wish without actually loading anything. So if we want to encapsulate the loading process, how can we do that? We can try something like Elm. In Elm, your reducer can return a pair of new state and a command. Then this command represents a side effect, which later can result in more incoming messages to the reducer, as you see on this inner loop on the diagram. So on the plus side now, the business logic is encapsulated, but the rest is not so good. We actually tried this approach, and it looked like this. Don't try to understand this. I'm showing it so that you get a feeling why we didn't go with this in the long run. It is difficult to understand, and it's mixing up the otherwise separate concerns of state updates and command execution. On top of this, it's still possible to set the state to save, for example, to reflect saving without actually saving anything. Same problem. Can we do any better? So what we did instead is we added an optional component, the actor, which can act as a middleman between the wishes and the reducer. The wishes then no longer affect the state directly, but trigger some execution, which in turn will send effects to the reducer. Now, this is an optional component, so if you don't have anything asynchronous, you can still just use the feature with a simple reducer. In code, we still have the same state, but a public API of the feature, the set of wishes, now only contains a single one, that is to start loading the data. And now the multiple steps of this loading process are represented as effects and can only be used internally by the feature. The reducer doesn't need to change. And now we should define how to get these effects from wishes. So we create the actor, which will have a reference to the service call. And when invoked, it can decide what to do based on the current state and the wish. And it's expected to return a stream of effects. So when it receives the load something wish, it will execute the asynchronous service call, map its result to the success effect. It will also immediately emit starter loading and the failed effect if something unexpected happened. And again, all we need to do is just pass the actor to the constructors to make it work. Another important part is how we handle events that should be consumed only once when they happen. So coming back to this example, imagine that something actually failed, and we set the error flag to the state to true. And then somewhere we get this state, and if it has error, then we want to show a toast based on this. So we show the toast. And then we leave the app, the activity gets destroyed. After some time we come back to it, and guess what? We see the toast appearing again. Why? Because the toast is based on the flag in a state, and the state is still the same. Nothing changed it, and it still contains the flag set to true. Now obviously when you come back to this app, it's the last thing that you would expect, just a random toast popping up that some error happened. So now you have to indicate to the feature that you have consumed that event so that it can reset the flag. And that's a bit inconvenient. Also, what happens if you have multiple subscribers to your feature? Which one should tell the feature to reset the flag? And what if you have more than one of them doing that? Can it result in, let's say, race conditions? That's also not cool. Key point here to realize is that the state is not a good place to store something that is transient by nature. And now it becomes really handy that our feature is more than just a simple reducer, and we can add some additional components to it, which is exactly what we did. And we added a second output channel to the feature, the news channel. And we can have this optional component shown with blue, the news publisher. It has full access to the execution chain, and it can see what incoming wish resulted in what effect, which resulted in what new state. Then it can fire events in the news channel on a one-off basis. And whatever it does is not stored in the state. That's the key point here. So let's add news to the feature. We will have this one kind of event when the network fails. The news publisher, when invoked, will receive the original wish, the effect, and the state that it resulted in. And it's expected to return either news or null. For now, let's just emit the corresponding news if the effect shows network failure. In all other cases, just return null. Otherwise, you can implement any other complex logic here. The only thing left to pass is, again, the news publisher implementation in the constructor. So now we can subscribe to the news channel instead from the feature and base the logic on that. So this event will fire only once and not change the state itself. And we will show the toast correctly only once. Let's get back to another problem which relates to how we use our features, pretty much any other component. I'm going to discuss this in 3 sections, but in the end they are just different aspects of this bigger problem. The first one is Dataflow. So consider this. We already said that MVI usually comes with unidirectional Dataflow. Why is this important? Let's see what happens if we were just to call a method on this feature to show our intent, and we would get a new state as a return value for that method call. But what if there are multiple other components that somehow connected to this feature? This approach would mean that all these components could each have a possibly different version of the feature state, based on the last time that they called this method. And there's no single source of truth here, and that can lead to state problems. So what we can do instead, we do not expect a new state as a return value for this method call. We just keep giving intent to it, and only if we are actually interested in it, we keep listening to the feature's output channel. Now we have a single source of truth. And if we want to add additional components, they will all automatically receive the latest state. Another nice thing is that it's easier to understand possible data flow between components. For unidirectional data flow, Rx kind of lends itself. So you have an observable stream, and any number of other components can subscribe to that. How can we connect them? So what if we started thinking about our components as reactive inputs and outputs? We could make them observables and consumers then just connect them with subscriptions, which is exactly what we did. And instead of reinventing the wheel and creating new interfaces, we just reused the ones coming from RxJava. To keep it lightweight, we decided to declare outputs as observable sources of some type. And for inputs, we went with the consumer interface. So in the case of a feature, it could define what wish it can receive and what state it can output. And then we can make it a consumer of wish and an observable source of state. And in the case of the view, it would consume the state and it would be an observable source of wishes to the feature. And this is a pretty common approach, but there's a problem with this. Coupling. Because in this setup, the view knows just too much about the feature. It relies on the state and the wish that it defines, which means that it's difficult to reuse on somewhere else. So what if instead we would say that the view would define its own view model that it could render, and it would define the events that it could trigger, like, let's say, when a button was clicked. And this is a much better approach because it gives us a lot more freedom to choose how we would like to create this view model, or where would we like to send this event to. So now we have separated the view and the feature. We need some transformation in both directions. We need to transform state to view model and the events to wishes. So how can we do that? We tried to create a layer here called the boundary to do this job. We even standardized this as an interface with generic types for UI event and view model. And you could notify it of a UI event happening and subscribe to the stream of view models. But it was kind of a short-lived thing because we realized that this wasn't flexible enough. Because what happens if you have a view that should display a combined state of 2 or more features? Or what happens if there's no view and just 2 features talking to each other? Or if there are some additional components that are interested in the state updates or the view events? Obviously, the boundary type in its current form is a bit too rigid to support all those cases. And just to make things worse, our implementation was scoped by Android activities and fragments and didn't really work with more general cases. So before speaking about how we solve this, let's see the third subproblem here, which is scoping, because it's a solution to an answer to both of them. What kind of scopes do we have? On the top level with blue, you can see the whole of the application's lifetime represented as a scope. And inside that scope, you might have some shorter-lived ones. So the gray ones, for example, could represent the scope of a user session. And at the next level, just for simplicity, you could represent individual screens as scopes. You might have many more levels than this. But for just the sake of the example, let's stay with these 3: application scope, user scope, and screen scope. And let's add some views, features, and other objects here. So if you want to keep an object that lives longer than the current screen, but not entirely a global singleton in the app, then some DI frameworks help a lot with that, to create scoped singletons. But what we want now is to connect some reactive components that live in these scopes, and nicely dispose of those connections when the scopes go away. For example, we might want to connect to this view, to this feature, but only until the view is there. Or we might want to connect this feature to the top one, but only until the short-lived scope is alive. So since we already employed Rx, let's see what else we can do there. Going back to the example where we have an observable source as an output, and we have a consumer as an input, and we connected them with a simple Rx subscription, we needed a generic tool that would help us with automatically handling when to create these subscriptions and when to dispose of them. And we named this tool, we created the binder. Thanks to Kotlin, we can have some syntactical sugar here and just say binder.bind output to input. And this will create a subscription for us between the source and the consumer. It works now because both the source and the consumer are working with strings. What happens if I now change the consumer so that it consumes ints instead? Obviously now it wouldn't compile, but I can add that transform it from string to int, and I can now use this transformer in the binding with some syntactical sugar again, thanks to Kotlin. Going back to this example that we had earlier, this is how it would look in code. So we would bind the view to the feature using a transformer. And we could bind this feature's output to the view and the green components. And in just 4 lines, we describe the reactive connections in this small subsystem. There are a couple of additional benefits here. First, we can reuse the same output from any component to bind it to a new one without having to modify a single line in the component itself. So here, I just added this analytics tracker shown with blue on the left, which consumes the view events for tracking. And I didn't have to change a single line in the view itself. I'm just reusing its output channel for another purpose. Another thing beyond the syntactical sugar is that the binder is fully lifecycle aware, but also it's in no way tied to Android. So here, as I create a binder, I pass in a lifecycle instance to it, which is not to be confused with Android lifecycle. There's an interface from the library. And what it does is that you have this source in the consumer here, and the lifecycle can have begin and end signals multiple times. And whenever the binder receives a start event or an end event, it will automatically subscribe or dispose of that subscription, and it can do it for you as many times as you need. These lifecycles can be created from Android lifecycles or from other observables, or it can be again triggered manually, which gives you a lot of flexibility how to define what concept defines your scope. It can even be your dependency injection scope. So in this example, we can take the feature from the app scope and inject it in the gray user session scope, and they will be connected by the binder there. Or we can take the same feature from app scope along with some more components from the user session scope and inject them to the current screen scope where the binder will connect them with the view, for example. In the meanwhile, the connection we created in the larger scope, shown with gray, is of course still alive between the two features. And when those scopes are destroyed, binder will make sure that these subscriptions are also automatically disposed of. To sum it up, the binder solves the problem of coupling and scoping together in a clean and elegant way. It lets you think about your business logic in terms of completely decoupled reactive components. They are only connected together for the duration of the scope that you define, and the binder is the glue that holds them together. On the code level, it gives you this very concise, high-level overview of data flow between your business logic components. While this one is not so much of a problem, as it's a bonus solution, a very cool concept that comes from Redux is its middlewares. In Redux, you can write generic functionality that you can use as layers of an onion. So if you have your state machine, then instead of talking to it directly, you can add a layer that will, for example, log every intent that goes through it, or every new state that comes out from your user. And you can easily compose these layers. Middlewares in Redux-like architectures usually only work around the state reducer, but we want to step further ahead. So take the consumer interface, which has this one method, accept. And if we create this middleware implementing the consumer interface, we need to implement accept. So let's take another consumer, and we will just wrap it around and just delegate the method call to it. But at this point, we can do whatever we want before or after we do that. So if we want, we can add a logging statement here, for example, without modifying, again, a single line in the original consumer. Or another cool thing is that you can have a time trial debugger where you can go back in time and replay your state changes. For that, you definitely need to save the element first somewhere, and you could do it here. And again, you can compose these layers. So since we already said that all our reactive components are consumers, it means that we can automatically add logging and time trial debugging functionality to all of them. And we actually have a working time trial debugger that you can find in the library. And it works just as much with state machines as with any other object that implements consumer interface. So let's sum it up where we are now. We solved the state-related problems with immutable state and state reducers. We added actors to encapsulate side effects in a feature. We solved the problem of one-time events by adding a separate channel to the feature. On a larger scale, we solved how to connect our components in a decoupled way using scoped reactive bindings with the binder. And as an added bonus, we can have logging and time trial debugging middlewares on all of these bindings. And all of this is available on GitHub for you to try. So you can find our feature implementations in the library with the binder, the middlewares, and the time trial debugger. But let's stop for a moment here. So even though I spend most of the time talking about MVI core, it's not everything what this talk is about. I spent so much time on it because it was the single most impactful approach in the last couple of years, which you can consider done and the proven success story. But there are things which even MVI core does not, of course, and cannot offer a solution for. To see just how far we've got, let's zoom out for a bit and have a look at the bigger picture again. A step from having God activities to having MVP allowed us to separate UI and business logic. Well, not too much, but to some extent. We did a small detour with clean architecture, only to realize its separation of layers is not in the right direction, at least for us. We realized that our problems were mostly state-related, and we went down a longer road with MVI core. And beyond state machines, it also helped us to completely decouple UI, business logic, and other components by using the binder approach. And most importantly, our state machines, the features in MVI core, allowed us to standardize how we implement our business logic. So what does it not solve then? I'd like to mention two problems and a teaser of what we are working on currently. One problem is that all the apps we have, of course, have their own different UI. So take a look at these screenshots, for example. They are from different apps, all containing a card swiping component, but they are not exactly the same. So we first approached this by sharing only the MVI core features between these apps and rewriting the whole UI layer every time, which was, of course, time-consuming. And wouldn't it be just so much better if we could also provide the default UI that just works out of the box and customize it later? And another problem is that once you have complex enough screens, a single feature will, of course, not suffice. So a naive approach to this is to create lots of separate features and somehow wire them together. What you see here is we got to a point where there were screen implementations containing 20 to 30 features with their own interactions, and it required lots of wiring. It was difficult to understand. And it was difficult to think about all the possible interactions between these features that needed to be tested. The bindings configuration started more and more to look like this. So even if a binder statement saves you quite a few lines of manual RX subscriptions, if you have this many of them, then you start losing the benefit of easily understanding your system. And this is not the fault of MVI core, but rather it looks like we are missing a vertical structure here. The key point to realize was that we were thinking in screens, and we tried to describe the complexity of a busy screen in code as if it was one big piece. And we needed to unlearn that. Instead, we needed to break down complexity to manageable chunks and use smaller building blocks. And what I'm about to show you here is only a very quick teaser of what we are working right now. So we investigated quite a few approaches and finally started a journey with Uber's RIBS architecture last year. We created a fork of it and added many extra features along with reused boilerplate code. But did I just talk this lot about MVI core to say that we are switching to something completely different? It's quite the opposite. We are not replacing, we are in the process of merging two things that solve different problems. So in case you haven't heard of it, an oversimplified summary of RIBS is that it helps you to think about your application in terms of business logic-centered tree structure. And this tree structure means that we can break down complexity to a hierarchy of simpler nodes. Every node knows just enough it needs on its own level, so they stay simple. In addition, every node is an encapsulation of both its immediate business logic and its UI. They also implement their own local navigation, so we don't need to implement global navigation. They have their own local dependency injection scopes. And the best part is that it plays together with MVI core just beautifully. Every node in this tree is naturally of an ideal size and scope for both the state machines and the reactive bindings. The whole topic is a goldmine of information and deserves its own talk, especially the parts what we modified and where we improved the original library so that it fits dating apps just as well as ride-sharing ones. We have a preview version available, and we are aiming for a version 1.0 in the upcoming months. We will come back with lots of updates, documentation, and tutorials, so stay tuned. I hope you found this talk interesting. If you'd like to read more about it, you can find articles on badootech.badoo.com about the architecture and demo of the time-to-roll debugger. And of course, don't forget to check out the libraries on GitHub. I think that's all for today. Thank you very much.
Thank you very much. Few minutes for questions. If you have questions, it's time. Any question? No. Thank you very much for the talk.
Thank you.